And that's it. This is our API. It's that simple. So actually we don't need to develop anything more to run this API, but we need to package it as a Docker file. This starts to become a little bit familiar now. We need to make sure it runs as a Docker file. So we put together a Docker file. We use another base image this time. We're not interested in Shiny, but there exists a very good base image for Plumber. We set the work directory as before. We copy in the files. We expose the port. It's port 8000 is the default now for Plumber, but you could change that to anything you like. The two next lines that called run, they are used if we want to also build the model as part of building this Docker image. We could have those lines in, but we could also do that before we build the Docker image. And what you want to do in different cases will depend a little bit. I think typically I would build the model in one workflow, one Docker or something like that, and then I have another one to deploy it. So you can ignore those lines for now. And the only, and as CMD, and if you remember, CMD means what should it run when it starts as a container? What file should it run? And we just specify our R code file here. But then you might think a little bit, okay, this R code doesn't do that much, does it? If you loaded this, if you type this into R, not so much would happen, right? It would read a model, it would define a function, and then it would exit. There's nothing else to do, right? So some magic is going on here. And that magic comes from the Plumber base image. What it does is it specifies how to start actually the Plumber package. It will start up, it will run, it will wait for connections on port 8000, but you don't need to worry about that because it's all in the base image. So the only thing you need to specify is the file name and path to your API definition. Plumber takes care of the rest. So you see, I mean, we don't need to write basically any code to do this. We just specify some comments and then use this image. And as before we build that, we build Docker build. We can run it with Docker run. And in this case, I have run with curl. Curl is a command line tool to get web addresses. Most of you have probably used it at some point. We can use that to call our local host, putting in a parameter of caret equals 0.5. This is the input, this is the endpoint, this is our API, and this is the response that comes from Plumber. It's a JSON object with price equals something, which is the prediction then of this price. Good. That's it for deploying APIs. Few notes. When we do this in production, we need to be careful and think about security. But there are different ways we can protect this. And in some cases, we can actually protect this by means of networking. So I worked in a case recently where we had APIs, but they were not supposed to be called over the internet. They were only being called from the same cluster. And in that case, we can just make sure the configuration is such that they can only be called from the cluster. And then we don't need any extra security measures. The cluster will take care of that. You could also, if you have a proof of concept or something like that, you can have some thing that you do yourself with a simple API key that your code will actually test. Is this API key okay or not? I wouldn't recommend that for production, but it might work in some cases. So the most robust way is to, again, as with Shiny, put something in front, something that is secure and it is designed for this purpose. And in this case, we usually call that an API gateway or similar. And it will work similarly to the Shiny case. It will intercept the calls. It will verify the authenticity. So in this case, we typically use API keys. So it will check the API key, is it valid? And can it be used to call this function that it is being called for? And that sort of thing before it forwards the request to our actual API. So it has some sort of registry of valid keys and that sort of thing. And typically it will also collect statistics, so we can see the usage of our APIs. We can see how different customers are using them, etc., etc. We might even bill based on usage, or we might put limits, so this API can call this API key can call this API only 1,000 times per week or something like that. So we need to think about, if we are making a public-facing API, we need good security measures in place. We need to be aware that some people might try brute force attacks, trying millions of API keys to see if they can crack it. Denial of service attacks, that's just sending a lot of traffic, trying to break the system, that sort of thing. And in our platform, IBM Cloud, the service that does this is called API Connect, but there are similar capabilities in all the major cloud platforms that you should be aware of. Right, so I promised to come back to the performance question. So let's handle this. Let's settle this once and for all. Okay, maybe we can't, but I'll put in my 2 cents anyway. So is R slow? And I would answer that with some counter questions. Compared to what? That's the first thing. What are we comparing with here? And so and the second question is, what is actually too slow? Because it has to be translated to some business requirement or some business need. So for instance, if we're talking scoring again, how quickly does the system need the score? And as I mentioned, if you have a system where and we call that typically the latency. So what is the time that our component can take to make the prediction? And if we have requirements that should be done in 10 milliseconds, well, okay, then R is probably not the right choice. You need to be on the mainframe and writing that in COBOL or something like that. Then it will run in 2 milliseconds. That's perfectly fine. We can do that. But many times it's not like that, because no one is going to, for instance, no one is going to act on this until 5 minutes later at a minimum. And in that case, it doesn't matter if it takes 10 seconds or 2 seconds to do this. So I would always try to urge you to think about what is the actual requirement in terms of speed. There are also several things we can do, and we'll look at that on the next slide to actually improve the speed and performance. But I want to highlight 2 articles that might be interesting. The one to the top there, it's a blog post from ThoughtWorks, very skilled people. It's a case study. They did a project for a customer that had some long-running analytical process. I think it was running on Hadoop. It was taking hours to complete. And they rewrote that work completely in R, and it took seconds to run. Because they made a clever mechanism of dividing the work into multiple chunks and having different R processes working on those chunks on a big enough machine, and then combining the results at the end. And that's a good counterexample where people say that R is really slow or R can't handle big data, because this was big data. So I urge you to read this article. It will provide ammunition to to talk to those people. Another thing that came out pretty recently is the one to the bottom there, timing the same algorithm in R, Python, and C. It was from the blog WinVector. They were working on some package and wanted to see, so they wrote the exact same algorithm in R, Python, and C and compared the differences, and there are some surprises in there. So, but one thing that we learned that really confirmed is that when you write for loops to go through like vectors and looking at each index, it's really, really slow. But it's also slow in Python to do that. I mean, you would never want to do that. You would want to work on vectors if you have vectors. And in that case, it's comparable with Python and R. C, of course, is faster for those type of things. It can run for loops extremely fast. And just last week, Joe Cheng, the CTO of RStudio, gave a talk at the RStudio conference on using Shiny in production. So if that is a topic that is of interest to you, and it might be since you're actually here, you can check out that talk. And he said one thing, or wrote actually, R can be slow and is single-threaded, but it's probably less slow than you think. And that mirrors my experience, that we can improve the speed of R, we can also scale it very much. And I'm probably running a little bit out of time, but I'll highlight some of the things we can do to improve the speed and throughput of R code.